chapter 11. Here we go. Unsaturated hydrocarbons. Alkenes, alkynes, and then at the end of the chapter we'll get to aromatics. So I might not even mention them today. We might get to those on Wednesday. But these are all unsaturated hydrocarbons, and they're kind of each one is a class of their own. There are some similarities. Alkenes are going to have this customary suffix ene, and they're going to have a carbon-carbon double bond in them. Alkynes are going to have the yne ending on them, and they're going to have at least one carbon-carbon triple bond. Okay, because alkenes, it's a carbon-carbon double bond, the simplest one is eth with two carbons. You got to have two carbons to have a carbon-carbon double bond. So there's no such thing as methene. Okay, methene is not a chemical. It's a misnomer. Methene or methine. You start with eth. And what you're seeing here is an IUPAC name and a common name. IUPAC name, common name for this molecule. We'll come back to and talk more about those in a minute. All right, here are some structural formulas. Here's the structural formula of an alkane with two carbons, ethane, that you're already familiar with. Ethene with a double bond, carbon-carbon double bond, and ethyne, a triple bond. So these are structural formulas. Molecular formulas. You can see right away we don't have, this is CnH2n plus 2 for alkanes. You don't have that, you'd have a different formula here. We really don't talk about a formula that will be very useful as we go along and look at bigger ones of these. Condensed formula, CH3CH3, was sufficient for alkanes. In the alkenes, we're going to put the double bond even in the condensed formula. And maybe I'll try to use a couple more examples. Likewise with the triple bond for the alkynes. This word aliphatic, I don't use it a whole lot. You'll see it. See it here. You'll see it in your book. Aliphatic, we're talking about more or less the open chain version of this cyclohexane. Wouldn't necessarily. It's a ring structure. It's in a ring. It's not an open chain. But just to mention it. Bond angles. Would be nice to have more molecules here, but I have any more here. It's somewhat helpful. Boy, those things bounce. Yeah, what I want you to see here here's ethane. You know, there's that molecule right there. And I mean, they're doing a pretty good job of depicting it right there. But I just want you to see that it is a three-dimensional molecule. There's a certain amount of volume it carves out. But as soon as I go to this structure right here, I get a flat molecule. I've got a double bond right there. And I mean, this isn't just a consequence of the models. The model is mimicking the shape of this molecule. Obviously not to size, it's extremely small, but here it is depicting the arrangement of the nuclei with respect to one another, and we know this. I mean, you can freeze ethene and do an X-ray diffraction and say, yeah, the carbon is there and the hydrogens are there, and they're all they're flat. The molecule's flat. So we do have experimental confirmation of these shapes that I'm showing you. It isn't that we went out and bought a kind of a Lego set here and said, well, let's just call this their shape. These models are trying to mimic the actual shape of these molecules and do a pretty good job of it. So that is flat. And now the angles are different. Here we have our tetrahedral angles, 4 equal angles around this thing, and it's 3-dimensional. It's tetrahedral 109.5 degree angles. But here with this flat molecule, I've got an angle, one angle here made up of these 3 atoms, another angle here made up of these 3 atoms, and then another angle here made up of those 3 atoms, and I've gone right around that carbon, full circle, 360 degrees. So I divide that full circle into 3 equal parts, and you get 120 degree bond angles. I know one reason why I might fade out is because I walk away from my computer, right? So I got to keep my computer with me. 120 degree bond angles. And then if you look at acetylene, 180 degree bond angles. There's a triple bond. And now we're, if we go right to here and then back around here, we've gone full circle around that one carbon. 180 plus 180 is 360. It breaks that circle up into 2 equal parts, 180 degree bond angles. And the other thing I want you to notice is that 4 atoms here are in a straight line. 4 atoms describe a straight line. So when you see a triple bond, there should be 4 atoms in a row in a straight line. The 2 that make up the triple bond and the 2 atoms that are on either side of that triple bond. It's going to make a straight line. All right, take this up a notch. We now have 5 carbons, pentane. 5 carbons, we've got a double bond on the end, that's pentene. And 5 carbons here with a triple bond on the end, we have pentyne. Pentyne. And if I take that, I want you to kind of be able to imagine a bit what's going on here. Now, a minute ago, I had ethene up here, and I said it was a flat molecule. Well, I replaced that one hydrogen there with 3 carbons going off on a chain. Those 6 atoms are still in a plane. So this end of the molecule is planar, and then what happens, it reverts to the zigzag shape of an alkane after that. After that, we don't have flat thing, we have tetrahedral bond angles. So this ends up looking like that, but over here, everything around these 2 carbons is flat. So when we start going to draw structures, well, if I was going to draw I could draw it straight out there, or I could go like this. I don't mind doing that because I like to kind of I like to preserve, that's the word I wanted to say, preserve this flat, this orientation right here, where you got a double bond and then you got something sticking out at an angle here, at another angle there. And then you get on off here to just the way we would draw alkanes. And notice that since we've got a double bond here, 1, 2, 3, 4, we only have 2 hydrogens here and 1 hydrogen there. There's only 4 things around these 2 carbons. 4 things. Hydrogen, 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 and then the rest of that chain. Let's stick with this molecule for a second. If I were to do the line formula, there's my double bond. There's my 3rd carbon, 4th carbon, 5th carbon. 1, 2, 3, 4, 5. So there's your double bond. 1, 2, 3, 4, 5. So I put, that is straight, and then I'm coming out at that angle, and then I just start zigzagging like I would with an alkane. That's the line formula.
Which molecule is this again, I guess?
This is this one up here. This is pentene. Pentene. Now, let me call it by its proper name. This is, and we'll talk about why in a minute. It is actually 1-pentene. This is 1-pentene. So it really wouldn't be entirely accurate to just call it pentene, because I would be sitting there, and a chemist would be sitting there saying, where does the double bond begin? The double bond begins on the 1st carbon. So this is carbon number 1, 2, 3, 4, 5. We'll get into this. We're going to spend a fair amount of time on naming these in just a second. So just for now, know that that's 1-pentene. That's its structural formula. There's its line formula. Oh, condensed. We might as well do condensed. So I would have CH2 CH, CH2, CH2, CH3. Okay, so you can see how this part of the molecule, I'm going to write it as we have been writing condensed formulas, just writing them there. But this part right here, I've got a CH2 there, I've got a double bond, and then I have a CH right there. And then the next thing on that CH is a carbon. It's a CH2, and a CH2, and a CH3. So that's the condensed formula. So put the double bond in the condensed formula of a alkene. We don't put the single bonds in, but we do put the double or the triple. So let's look at this one right here. And again, if you don't get it yet, don't worry. We haven't explained it. This is 1-pentyne. 1-pentyne. The triple bond is on the end. So we would have something like this. We would have a triple bond right here. Now, I'm not done yet, but notice 1, 2, 3, 4 bonds around that carbon. So I don't slap hydrogens up on, so you don't go like you did in chapter 10 and put a hydrogen above and below every carbon along the chain.
Since it's already full with its 4 for this.
Right. You count bonds around the carbons and then decide how many hydrogens it needs. So here, this carbon, 1, 2, 3, 4, what do I put around this one? Nothing. Just move right on. So then it's going to be carbon, carbon, carbon. and I need 2 hydrogens there, 2 hydrogens there, 3 hydrogens on the end. Okay, so when I give you chapter 11 homework, do some real careful accounting of how many hydrogens. That's why you want to do these in pencil. You want to go back. Don't just assume it isn't, you're not getting graded on how fast you get it done, right? On how accurately you get it done. How accurately. So go along there and go through this. 1, 2, 3, 4 bonds. 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 Okay, line formula. I'm going to draw a triple bond. Remember, on the line formulas, we concentrate on the carbons and we ignore the hydrogens. So I'm going to do that. The next carbon, I'm going to bring right straight out of that triple bond. Because I told you a minute ago, I mean, that's what we've got here. Really, that's what you got. I'm doing the line formula of this molecule right now. So I got a triple bond, and then I got this carbon sticking right out. It's a 180-degree bond angle. So to the extent that we can, we like these formulas to kind of reflect the molecule. So this reflects it. So then, after that, it bends. So this is carbon 1, 2, 3, 4, 5. There it is. That's one pentyne. 1, 2, 3, 4, 5 carbons right there. And the condensed formula would be CH, C, CH2, CH2, CH3. All right? There's no carbon on that thing. Or no hydrogen, excuse me. There's no hydrogen on this. There's 1 hydrogen on that. So it's CH. These triple bonds are not to that hydrogen. They're to this carbon there. But we lead with the carbon, and then what's happening afterwards? Yeah, I wouldn't be surprised if someday you would see that, like that. HC, CH2, same thing. Doesn't matter. Either one would be acceptable. Is that all I wanted to say there? I think so. Physical properties. Remember, every chapter we're going to talk about, okay, alkenes, what are they? How do you name them? How do you draw them? How do they react? We'll do that with alkynes as well, but we're really going to concentrate on alkenes. And then I'll expect you to kind of recognize that alkynes are very similar. They can react in very similar ways, but more than once, where an alkene might react with bromine, with one molecule bromine, it will react with 2 molecules. Alkynes will react with 2 molecules of bromine. We'll try to make that connection later. But what are the properties? They are nonpolar molecules. Remember, alkanes are nonpolar. And one of the consequences of them being nonpolar is they don't dissolve in water. They do dissolve in other nonpolar molecules. So alkenes will dissolve in alkanes. They'll dissolve in one another because they're all nonpolar. Gasoline has a lot of alkanes in it. It probably has some alkenes in it as well. I'm not sure about that, but it's mostly alkanes. But gasoline would dissolve pentene or pentyne. Those would be soluble in gasoline because they're all nonpolar. And we saw in chapter 10 that as the molecular weight or the size of the alkane increased, the boiling point increased. We're going to see that here. If you focus on these here, get this back down. Yeah, there we go. I'm going to try to make that bigger. These three right here are the best three to focus on because we have a 2-carbon ethene, 3-carbon propene, 4-carbon butene molecule. So what's happening? We're adding a carbon to each one of those. That's increasing the size and the weight, the molecular weight of that molecule. And the boiling point is increasing. -6 is a much bigger number than -103. So we go from about -100 to -50 to almost 0. So we're increasing. Boiling point is going up as the molecular weight goes up. That's all I generally expect you to see. Later on, we'll be comparing boiling points of alcohols to some of these molecules, and we'll get a little bit deeper into that. But just for right now, that's enough. Boiling point increases with increasing molecular weight. Okay, so we want to get into now IUPAC naming system. I told you in chapter 10 that you're laying the groundwork for naming in a couple of ways. One, you learn these prefixes. Meth is 1 carbon, eth is 2, prop is 3. That's going to stay the same here. Okay? Eth is 2 carbons, prop is 3 carbons, eth 2 carbons, prop 3 carbons. So those 10 prefixes you learned in chapter 10 transfer into all the other chapters. Not just chapter 11, but all the other chapters. The other thing that transfers in are the IUPAC rules. All right? What's the first rule in IUPAC naming? What's the first thing you do if you want to name an organic compound? Yeah, the parent name. And where's the parent name come from? Longest chain. So the very first thing you have to do is look at the structure and find the longest chain. Okay, so those rules, we're going to bounce down through those, but we have to figure out how to incorporate a double bond. How do we handle a double bond in the name? And this is one way. I mean, this is a way. We put that on there. Number from the end that will give the first carbon of the multiple bond the lower number. Prefix the name with the number of the first multiple bonded carbon. And then prefix branches and substituent names as for alkanes. All right, that's a lot of words here. Let's understand how we do that. Let's look at that molecule. The top molecule, and find the longest chain. How long is it? Now the longest chain has to include the double bond. Five. Do I hear 6? 7? 7.
Is the double bond 2 different? You count that twice?
No, you only count it once. And remember, when you do it, imagine you're using your finger and you're staying on the line. You can't deviate and come back to it. 6? 6? 7. Kevin? 7? 7? Where do you want me to start, Kevin? Right here? 1, 2, 3, 4, 5, 6, 7. Okay, so, and look, I'm not going to just leave that on there. 1, 2, 3, 4, 5, 6, 7. Okay, now 7. So So what is the parent name? Heptene. Heptene. Okay, now, next thing is to figure out which is carbon number 1. Is that carbon number 1 or is that carbon number 1? Why here, Kevin? Okay, it gets you here faster, right? 1, 2, 3. If I start here, said that's 1, 2, 3, 4. I don't get to that until I get to the number 4. So this is it. What about that one? Could that be carbon number 1? Yeah, it doesn't matter. 1, 2, 3 or 1, 2, 3. So we stuck with that one. 1, 2, 3. So we're going to use that number in here. We're going to put that number in front of heptene because that tells us, that double bond could be right there. Could have been. We'd have to change the hydrogens. It could have been there. It could have been here. There's different places it could be. So there's not just one heptene. This one happens to be 3 heptene. So that means this is carbon number 1, number 2, and that's number 3, which means that makes that number 4, number 5, number 6, number 7. Once we decide what carbon number 1 is, it determines the number of every carbon in the chain. You don't renumber. You don't come back over here and say, oh, that's a 2-methyl because it's close to that end. No. That is the primary end of this molecule, and it numbers all the carbons.
Can you explain why you got 3 again?
Okay, because this double bond begins. Where does it begin? It begins on the 3rd carbon.
Yes.
That's where the 3 comes from.
Okay, yeah, never mind.
I'm numbering. What that number associates with is this. So I'm not saying hept3ene. I'm putting the 3 out in front of the name, okay? But that's what it really is. It's hept3ene.
So that's just the location of the double bond.
That's the location. That's where it starts. That's where the double bond starts. So I don't have to put 3, 4. I know that the double bond is between 3 and 4 because you told me it started on 3 and it has to go to the next carbon. Okay, now let's see what we left out. We left that out and we left that out. The other 7 carbons have now been accounted for here. Okay, this isn't an alternative way of naming it. I'm just pointing out that this 3 is reflecting on that ene. It's telling you where the ene is. Okay, so what is this? It's an ethyl. And what is that? Okay, and where is the ethyl? It's on the 3rd carbon. Where is the methyl? Does that cover it?
What about the other one at the top? Do you count that one as part?
Okay, yeah, Leah, that's part of this.
Okay.
Okay, so it's not a diethyl. This is not a diethyl molecule. It looks like it. You say, oh, there's 2 ethyls. No, I've already accounted for one of them in heptene. Don't double count or don't double count carbons in your name. I've got 7 carbons there, 1 there, and 2 there. So 2 and 1 is 3, and 7 is 10, and there are 10 carbons there. If I called it a 3,3-diethyl heptene, I would have 12 carbons in there. There's only 10. All right? So you can see I only drew lines around the stuff that I did not include in the parent name. Those are substituents. That is not a substituent. That's part of this. All right, there's its name.
And are they all going to be all that long? Like, extra one, this chapter?
Is this chapter going to be extra long?
Like, are the names gonna be extra duper long?
Probably.
Okay, great.
Yeah. So when you write down your parent name, make sure you have a lot of room to the left. Okay?
Okay.
Don't write it down next to the margin on the left. Write it more towards the right and leave room for everything else. Okay, let's take a look at this one. It's the longest chain. 6. Got 6 carbons right in a row. So the parent name is what? Hexine. You got a triple bond. All right, we got a triple bond right there. Okay, now, where does the triple bond begin? Carbon number 3. And notice that it doesn't matter if I go 1, 2, 3. There it is. I could go 1, 2, 3. And there it is. It's right in the middle. Which one is going to be carbon number 1?
See left and on the left,
Over here on the left? Why?
because it's a halogen wall, so you have to do that which precedence, so you start with that.
Okay. We've got a substituent over here. Bromine, or a bromo group. And we are going to favor this as carbon number 1, 2, 3, 4, 5, 6, because we could go either way as far as the triple bond goes. It doesn't matter. But the bromo group, we want to give the smallest number, the lower number to. So we will start on the end. Here's where the substituent is considered, but it's not favored. Trying to think of an example. I mean, if we had an example where we had a real long chain over here and we had a bromo group right next to the other end of this chain, you say, well, boy, I could give the bromo a number 2, but that is going to give the double bond a number 8. Nope. This takes precedent over any substituent, okay? So we get to the double or triple bond first. Then we consider the substituents. The substituents are not going to take favor over a double or triple bond. So the bromo group is on what? 2 bromo, 3 hexine.
So how did you get bromo again now? It's just,
Bromo? Well, the halogens are, we call them fluoro, chloro, bromo, or iodo.
And then it was,
That's just its name.
okay.
Yeah. Bromine, this is bromine.
Yeah, so then you have to add the suffix on it, right?
Right. And that is a bromo. A halogen on the carbon is chloro, fluoro, bromo. Okay. Go ahead and figure that name out. And I'm going to pick a row here, and someone has to answer. Did you guys already do one? No, you didn't do it. I'm going to ask for a volunteer from one of the rows. Figure out the longest chain and the full name of that molecule. I tell you what, we'll mix this up a little bit. Who thinks they have the parent name? Yes. Hept? 7? Nope.
It's not hexene?
It's hexene. Okay, let's figure that out. What is the longest chain? There is a long chain right here. 1, 2, 3, 4, 5, 6, 7. Was that where you got 7? But that did not include that double bond. It went right past it. The chain has to go through that double bond. So you have to start here. 1, 2, 3, 4, 5, 6. All right? So the longest chain that includes the double bond is only 6 carbons long. So that means that has to go through the double bond. If you're going to call this an ene, if it's going to be a alkene, then that double bond has to be in the chain. Even if it's a shorter chain. And it is a shorter chain in this case.
So to be accepted as an E, it has to include the double bond. Okay.
Has to include double bond. Okay, now where does the double bond begin? 1. It begins on carbon number 1. If it's on the end of the molecule, then that end is carbon 1.
So it always has to start where the double bond is?
Well, the double bond could be further in, but you have to, the previous ones we started from the end closest to the double bond. The end closest
So
to
you
the double
start
bond
where
here is 1.
It is closest.
Yeah. Okay, we're kind of doing this together.
It's okay, somewhere in the river.
So we left out an ethyl and 2 methyls. So where's the ethyl? 2 ethyl. What do we do with the methyls? 4, 4. 4, 4. Now what? Dimethyl. Dimethyl. Look how much you have to think about. And so this. Let me fix this up here a little bit. 4, 4 dimethyl dash 1 dash hexene. Okay?
So then the ones that you circled, what about those?
So there's dimethyl.
Those, Leah, these 2 are here.
Okay, and then the first one, where is that one? Okay,
They're all there.
okay.
Is dimethyl not supposed to go first because it's in ABC order?
Okay, good question. We are alphabetizing off of the first letter of the name of the substituent, not the prefix. Would you put dimethyl in front of ethyl? No. No, ethyl always comes in front of methyl. Doesn't matter how many methyls there are. Ethyl precedes methyl. So alphabetize off the name of the substituent. Isopropyl goes off of I. Propyl goes off of P. All right, butyl, B, etc. All right, yeah. So go back and look at those 6 rules, and it tells you all of that. It says don't alphabetize off of these prefixes, off the name of that. Good questions. You see how this sorts it out? When you actually do something and have to kind of wrestle with it. Okay, there is such a thing as a molecule that can have 2 double bonds in it. We had hexene just a minute ago. Here is hexa, and look at here. We put the di, 2 enes, 2 double bonds. So it's 2, 4 dash hexadiene. It's not 2, 4 dihexene. We're actually inserting that prefix right in the parent name. Hexadiene. You can have a triene. 3 double bonds in a molecule. What train? Tetra? You could have a tetra. Okay.
What's the max you can have?
I don't know.
So
I don't know.
No more than two.
If you get into some,
As less as possible.
I mean, if you look at pharmaceutical drugs and you look at their name, you think these names are long? Oh, man. You know, they'll have heparin. Heparin. And then you go look at the IUPAC name of heparin. And it's several lines long, all in parentheses. Okay? That's the IUPAC name. They're trying to name everything that is on that molecule. Heparin. I was just looking at heparin yesterday. I had some other reason to be thinking about that. And I guess the World Health Organization recommends that heparin be available in like every hospital. It says it's one of the least dangerous medications and very useful one. And let's see, what's it do? Heparin. Okay, it's a blood thinner, or it delays blood clotting. Very good. Heparin. It's a natural product. We make heparin, but they also have it as a chemical or as a drug available. Okay. Before we look at, we'll come over and look at this slide in a minute, but let's just talk about cycloalkenes for a second. You know this already. That's cyclohexane. Let's look at that molecule. We put a double bond in there. We can't call that cyclohexane. What would you call that? Cyclohexene. We're going to change the ane to an ene. Okay, now right down below here, I'm going to draw the structural formula of this molecule. Okay, now let's work around this structure and fill in the hydrogens. I'm going to start right here. That needs 2 hydrogens. This needs 2 hydrogens. This needs 2 hydrogens. And this. So those hydrogens all have 4 bonds around them. But I've got 1, 2, 3 bonds here already. Where I've got a double bond, there is only 1 hydrogen. And where I've got this other double bond, there's only 1 hydrogen. 1, 2, 3, 4. 1, 2, 3, 4. Okay? So this formula for cyclohexane is C6H12. This formula for cyclohexene is still C6, but it's H10. 2, 4, 6, 8, 9, 10. So where we have a double bond, we've actually lost 2 hydrogens. Okay, now back to this slide that was getting a little bit ahead of ourselves, but here we have cyclohexene. You can see we got a double bond here. There's your 1 hydrogen, CH2, CH2. But now we got a methyl here and a chloro there. And what this slide is trying to show you, illustrate for you, is how do you count? Where do you start counting? You need to count. I mean, this is either carbon 1 or that is. But whatever is carbon 1, you have to, the other one is carbon 2. You have to go through the double bond. And do you go counterclockwise or clockwise? Well, it depends. You don't follow that rule. The rule you'll follow is count in the direction that gives you the lowest numbers. So if I start here with 1, 2, 3, 4, 5, I get a 5-chloro, 3-methyl, 5-chloro, 3-methyl, and the double bond is on 1, 2. If I decide that's 1, I don't count that way. If that's 1, I got to go this direction. 1, 2, 3, 4. It gives the chloro a 4. 5, 6. It gives the methyl a 6. So if I go clockwise, the substituents end up with higher numbers. If I go in the opposite direction, counterclockwise, in this case, if I go in this direction, I get lower numbers. So this is the correct name. So when you have a group of substituents and you could start at either end and it's not going to make any difference to the double bond that's in there, stop and consider if there is a way to name it with lower numbers for the substituents. I don't think I'm going to dwell on this, but this is a good slide to come back to and wrap your mind around and say, okay, what? Let's see, they're calling it that. Would I call it that? Yeah, it's 1, 2, 2 butene. You know, here's this is one we had earlier, I think. Yeah, that's just like, what do we have here? 1, 2, 3. 4, 5, 6, 7, 8. Yeah. Yeah, just come back and look at those. There's just some more good examples. All right. Man, we are just moving along here. Cis and trans isomers. Well, that's going to fall. There we go. What do I want to do here? I need another methyl group. Where I had another one. Oh, there we go. I was wondering where all these went. Thank you. Where do I want that to go? Yeah, I want that to go right there. All right. Okay. Now, I'll tell you what we're going to do. We're going to introduce the geometric isomers, and then I think I'll pick up on them again Wednesday after the quiz. This is important. Part of Chapter 11 is understanding what we mean by geometric isomers. We already introduced the idea of isomers in Chapter 10, but this is another class of isomers. So let me take this molecule. And you kind of look at this molecule and tell me what you would call that molecule. Based on everything I've told you so far, what would you name that molecule? How many carbons? There's a double bond. Butene. Butene? I like that. Butene. Is that the full name?
No, not yet.
What do we need? What else do we need in the name? No?
Something.
Butene accounts for all 4 carbons. 2. You need to tell me where that double bond starts. It starts on the second carbon. 2 butene. Everybody with it? Like that? Okay. Now, you're going to say, boy, that's a trick question. It is a trick question. What would you call that?
1, 2, 3, 4, 5, 6. Oh, over there.
What would you call it? 2 butene. Are they the same? Okay, the thing that I will challenge you with all semester long, and I'll say, are these 2 molecules the same? If they are exactly the same, then they don't need different names. Now, what's the test? The test for them being exactly the same is that they are superimposable on one another. I take this molecule and put it here, and I've got a methyl hanging out here where there's a hydrogen. And I have a hydrogen here where there's a methyl. And you might say, well, can't this just go around there? Can't. Can't do that. Alkanes can. Single bonds can rotate around the single bond. All right? Free rotation around a single bond. There is not free rotation around the double bond. So you can rotate this around here. So if I had a methyl coming out here and a methyl coming out here, and I was talking about butane, and I'd say, oh, the methyl's up here, this methyl's up here, I could just and push it down there, right? Because it can freely rotate around that single bond. There's no rotation. This is fixed. This molecule is fixed in this geometry. And this molecule is fixed in this geometry. And so what that leads to is that we need two different names for this. These are cis-trans isomers of one another. Cis-trans. What do we got here? Well, these two things, these two methyl groups are across from each other. They're on opposite sides of the double bond. Got a double bond here, and we got a methyl above it and a methyl below it. Cis, these are on the same side of the double bond. There's the double bond. I got a methyl above it and a methyl above it. So, here, why don't you, I might need you to pass this around firsthand. What we're talking about here while I draw these. Cis-trans isomers. These are geometric because of the geometry, because of their shape. They represent two different isomers, a cis and trans isomer. And so we've got this kind of orientation going around the double bond. I'll just draw two of these, just like that. And in this case, we had a methyl in one case. What happened? Why did that get small? Okay. Sorry. I mean, touch screen is great, but sometimes they're a little too touchy. All right, so we got a methyl down there. I got a hydrogen here and a hydrogen here. And that's your trans. 30, 40 years ago, if you wanted to call from London to, from New York to London, there was a transatlantic cable. Someone had put a cable, 3,000 miles or however far that is, underneath the ocean, and that was a transatlantic phone call. That's why the rates were so high. Someone had to pay for that cable. People who wanted to make phone calls between New York and London had to pay for that cable. That was transatlantic. So this methyl is across from that one. This is trans to butene. And we got another one here where the methyls are on the same side.
What does trans stand for?
Across, trans, I'm trying to think of another
Like opposite sides of
transfer. You transfer from one school to another. You want to transition. You're going across. But here, cis means kind of same side. This is cis to butene, and they are cis-trans isomers. And what this will lead to is what you'll end up with on occasion is a molecule that has a double bond in it, and you're trying to decide whether you need to use cis and trans in the name. And I think that's where I'll probably pick up on Wednesday after the quiz. Well, we'll come back to this. This is important, and I think it's kind of useful to kind of see it twice. You've been introduced to it. We'll come back and pick it up and ask the question, if I'm looking at an alkane, is it a cis or trans? Not every alkene needs that name in it. Yeah, if the double bond is on the end, well, I'm not going to give just a real simplified ruling to it. There's a couple questions you ask, and you can decide whether I need cis or trans in the name, and which one of those I need. Is it a cis or is it a trans? Here's chapter 11 homework. It will be due next Monday. So I would concentrate for the quiz, concentrate on everything alkane in chapter 10. And you can ignore anything that is not alkane, like alcohols and carboxylic acids. You can ignore that.
And this is going to be online as well?
No, the quiz?
No, this one.
Oh, yeah, that should be online too eventually. I'll try to get chapter 10 and 11 online.
No, it's just, okay, so I'm really OCD, to print it out again and do it again and turn in a good copy and then have my rough draft with my notes and reasons why. It's me.
That's what I like to do. It's so much easier.
If we get bogged down in the back, I think we next Monday. Hopefully we'll see.
Depends on how long the quiz takes, right?
Right. We need to do some.
What did we do?
Well, definitely make sure you see the grade. Okay, if you haven't seen it there, like, I'm going to try to get there by noon. You don't see the grade by noon. It's not very okay? So yeah, your grade in Canvas will be your trigger that the homework's ready to pick up. How do I stop?